Well, welcome back. In our last video, we introduced you to our analytical or algebraic way to evaluate a definite integral. We introduced you to the first fundamental theorem, and we talked about how a definite integral simply measures the area bounded by a curve and the x-axis and the two vertical lines x equals a and x equals b. And then to find that numerical value, we introduced you, like we said, to the first fundamental theorem here. And I'm actually going to add an intermediate step to that first fundamental theorem. I'm going to say this, okay, if we're integrating from a to b, little f, alright, what you get first is the antiderivative with bounds a to b, and then from there you evaluate with the b, and then you evaluate with the a, and you subtract them. So I like to throw in that intermediate step right there. But remember, capital F is the antiderivative of little f, and then we plug the upper bound in and the lower bound in and make sure we subtract them. Well, the big theme tonight is going to be just getting a lot of reps underneath our belt. I don't think we're going to throw too many new nuances at you tonight. We're just going to take what we've seen and what we've been introduced to and really just fine-tune and take it to another level. So just trying to deepen our understanding and build some muscle memory, so to speak. Just getting those reps underneath us. So here's a particular curve. And we're just trying to find the area that's bounded underneath this function between x equals 1 and x equals 2. So mechanically, my first step is to find the antiderivative. So I've got 1/3 x cubed. Remember, all I'm doing is adding 1 to the exponent and dividing by the new exponent. And the antiderivative of 3 is 3x. My bounds are 1 to 2. And then I'm going to plug the 2 in. So we got 1/3 2 cubed minus 3 times 2. Minus, and then 1's a very friendly number to plug in. And it's just a lot of cleanup here, you know, and it's one of those catch-22s. You want to go as fast as you possibly can, but you don't want to take the risk of making any careless mistakes either. So, and this is a lot of where those reps come into play, where we just need to practice doing it as quickly as we can. This 6 is really 18/3. So if I subtract them, I got negative 10/3. Minus, and that's really 9/3 right there. So if I subtract those, I got negative 8/3. So I'm thinking I've got negative 2/3 overall. Now, let's ask ourselves, does the negative answer scare us? And this is just where our common sense comes into play. I want you to go back and recall the function that we were integrating originally. We were integrating x squared minus 3, which if we visualize it, is a y-intercept of negative 3 down here, and then it's got a root here of radical 3, which is somewhere between 1 and 2. So we say 1's here, 2's here, and we're trying to find the area from 1 to 2, somewhere in there. All this means, and my picture doesn't do it justice, the fact that we got a negative answer here just implies that the area, the region below the x-axis was bigger than the one that was above the x-axis, and so our overall combined area was negative. Here in our second example, great opportunity to hit the pause button and try this one yourself and come on back and see if we went about the same path on this particular one. Now, an example, don't be afraid to pull that 3 out if that helps. Okay, if that helps. You don't have to pull it out, but I do recommend, I think it kind of cuts down on the chaos. So when you go to find the antiderivative, you're really focusing on that term only. So it's 3, and because it's the exponent's originally 1/2, I'm going to add 1 and get 3/2. Oops. So up here, the exponent was 1/2, and I'm just trying to add 1, which would be 2/2, and that's how I ended up with my 3/2. Now I need to divide by the 3/2, or I'm going to multiply by the reciprocal of 3/2. And let's see, the bounds are from 1 to 4. Notice the coefficients do clean up, and I've got 2 times the square root of x cubed with bounds of 1 to 4. We're going to plug in the upper bound first. So it's the square root of 64 minus, and then I'm going to plug in the lower bound. And by the time it's all said and done, let's see here. Square root of that would be 16 minus 2. I've got a net value or net area of 14. For our third example, we're going to sprinkle in a little bit of trig. We don't want to go too long without doing... Whoa, that is a bad integral sign. Let me erase that. Wow, I don't know where that one came from. Okay, let's go with a lower bound of 0 and an upper bound of pi over 4. So those are very friendly numbers. And we're going to integrate the secant squared function. So you'll notice they set us up with a really nice function whose antiderivative is tangent. Or you could say the derivative of tangent gives you the secant squared. And I've still got bounds of 0 to pi over 4. just keep reminding yourself we are going to plug in the upper bound first. So it's going to be the tangent of pi over 4 minus, now we'll substitute the lower bound. I've got 1 minus 0 for a grand total of 1. Now for the rest of tonight's video, I'm going to kind of bounce around and hit on a few odds and ends and just kind of tidy some things up. What I want you to watch out for is when you see a definite integral, we'll go bound 0 to 2, of something like this, absolute value of 2x minus 1. So how are we going to approach this? Well, hopefully you can quickly recall what we talked about in our last Good Morning Math, and you're screaming that we need to take a geometric approach. Okay? In other words, just to recap what we did say in Good Morning Math is that our algebraic approach where we use the first fundamental theorem does not apply to this one because we don't have an integration rule that applies to these absolute values. So we're going to take a geometric approach. And what I can say is, just by setting that function equal to 0, I can find that the x-intercept is at 1/2. So if that's a 1, I'm going to put the vertex right here. And it's going to be a fairly steep v. Okay, the y-intercept, I would just substitute a 0 in for x to get a y-intercept of 1. Alright, and let's see, we're integrating from 0 to 2. So I've got this triangle here, and then I need to go all the way out to 2. So a little taller here, and I'll make this one blue so we kind of have them color-coded, so to speak. And now we just need to work on the area of each individual rectangle. So the first rectangle has got, let's see, a base of 1/2 right there, and a height of 1 unit right there. So his area is 1/4, and then we need to add, let's see, I've got a base of 1.5 units, or 3/2. And what's my height? Well, I could substitute a 2 into that function and get a height of 3 units. And we'll put that all together. Let's see. I've got 9/4, I believe. And if I add those, I got a grand total of 10/4 is the area of these two triangles combined, which indeed is the value of this definite integral. So now I want to have a discussion about what's called signed area, or sometimes I like to use the phrase net area. Basically, we're saying, okay, we've got a region here that has an area of 3. Now this region from B to C, the area is still 1. But when we go to evaluate the definite integral, the answer is going to be -1, and all that means is that the negative implies that the region lies below the x-axis, okay? And then from C to D, we've got an area of 2, and from D to E, we do have an area of 5, whose integral would give us -5 as an answer. So let's go ahead and we'll practice a couple of these. The first one we could write down is, the integral from A to C of f of x. And we'll just agree that f of x is the name of this blue function here. Okay, so from A to C, how much net area have we accumulated? I like the word accumulated. It's almost like we're starting here at A and we're sweeping across and we're gobbling up area as we go. We've accumulated a net area of 2 units because I was thinking 3 plus a -1. Our second example, what if I wanted to go from A all the way to D? So what would be your answer to that one? We're starting at A, we go all the way to D. I've got a +3 plus a -1 plus a +2 for a net area of 4 units. What if I wanted to go from A all the way to E? How much area have you accumulated? Let's see, we've got our 3, our -1, our 2, and our -5. I believe that we have accumulated a net area of -1. And all that negative does is it tells you we've got more region below the x-axis than we do above. Alright, now let me try to spice it up here a little bit more. Let's try, what if I wanted to go from B to D? Lower bound of B, upper bound of D. How much net area have you accumulated within that space? -1 plus 2, I think we've got a net area of 1. What if I wanted to go from C to E? Lower bound C, upper bound E. Our net area is going to be -3, just because we do have a +2 plus the -5 net area of -3. Alright, let's see if you recall one of our properties. What if I wanted to go from E to B? Lower bound E, upper bound B. Do you see how we have a problem here that we need to address right away? What we're doing is we want to switch the bounds instantly. We want the lower bound to be b, we want the upper bound to be e, because we always want to integrate from left to right as opposed to right to left. But in order to do that, I need to negate the integral. Okay, so now I'm going to negate, and I'm going to go from b to e. So from, let's see, I'm going to go -1 plus 2 plus -5. That's going to be -4. But because I was negating that, I'm going to have a final answer of +4. So just watch out for that trick where they're going to try to mess with your bounds, and we're going to have to switch those bounds and negate our integral. Okay, so I did promise you that we're going to tackle a bunch of odds and ends here tonight, and no pun intended, but let's take a look at some odd functions. And just a real quick crash course from last year. Now, an odd function, the number one thing that I want you to know is that an odd function is symmetric with respect to the origin. Okay? And the way that I remember that is both the word odd and the word origin start with the letter O. A great example would be something like x cubed, whose graph, looks like this. Basically, everything in the first quadrant is a mirror image of something in the third quadrant. And that's how I know that that one's odd. Sine is another great odd function. Let's see, something like that. So everything in the second quadrant is a mirror image of the fourth, and everything in the third is a mirror image of the first, and so forth. Tangent's another good example. There are tons of great examples of odd functions. Basically, in terms of a polynomial, as long as, let's say 2x cubed plus 5x. He's an odd function because the exponents that you have, 3 and 1, are both odd. As long as each individual term is odd, then the entire function is odd. Algebraically, the definition was if I substituted a negative x, we would get a negation of the entire function, and that's how algebraically we proved that something was odd. Alright, now flipping the coin, let's talk about evens. An even function is one that is symmetric with respect to who? Hopefully you're screaming, y-axis. Alright, symmetric with respect to the y-axis. So x squared is a great example. When you look at that parabola and the fact that we could fold right on the y-axis and the curve would lay on top of itself. Or cosine's another great example of an even function. The picture may not do it justice, but it is there. And again, there's tons of examples. Basically, any polynomial whose exponents are even, don't worry about what the coefficients are. Something like x to the fourth minus 2x squared plus 7 would be even because each term has an exponent that's even. That last term has an exponent of x to the 0, so that's still even. And algebraically, we used to say if you substitute negative x, the end result is that nothing changes. You get the original function back, and that's how we used to prove it. So you're wondering, how does this apply to calculus? So I'm going to go show you some neat shortcuts here. Alright, so let's say, and again, we have what's called balanced bounds. Like, what if I wanted to go from -2 to 2? Those bounds are symmetric with respect to 0. If I'm integrating an even function, like x squared, what we have here is, let's try to visualize what's happening. I'm going from -2 to +2, and I'm referring to all this space here and all this space here. What we've got is you could just integrate from 0 to 2 and then double that answer because of the symmetry. You've got two congruent regions. This region here is congruent to this one. So might as well just go from 0 to 2 and double that amount right there. Why is that an advantage? Well, when you get to the number crunching, after you've found the antiderivative of x squared and you're plugging in the bounds, it's much easier to substitute a 0 into a function than it is a -2. So there's the advantage, and that's where you pick up some time. Now, what if we wanted, let's say we were integrating maybe x cubed. Beautiful odd function, right? You're going to like this shortcut even better. Let's say we were going from -2 to 2 this time. What would you get? Well, the answer would actually just be 0. Let's go ahead and look at that graphically. Let's see here. We do have two congruent regions again. You've got a region here from -2 to 0, and then you've got another region here from 0 to 2. The two regions are congruent. You just have one that's negative and then one that's positive, so when you add them together, they offset each other, and you end up with a big fat 0. So let's summarize what we've just tried to show you here. Alright, so let's say you're integrating from -a to a, and you're integrating an even function. What we're going to do every single time is we're going to integrate from 0 to a and double our answer. Okay, so that's our shortcut for evens. Doesn't sound like a big shortcut, but trust me, 0 as a lower bound is a big advantage. Now, if you're integrating from negative a to a and you're working with an odd function, best shortcut in all of calculus, the answer is 0, just because you have two congruent regions, one that's negative, one that's positive, and they offset each other. Alright, our last problem for the night is basically, it's the same concept, but we've put it into more of a word problem, and the problem says we want to find the area of the region bounded by the graph of, let's say, y equals 2x squared minus 3x plus 2. Okay? And it's bounded by that curve, the x-axis, and the vertical lines, x equals 0 and x equals 2. So I've taken the liberty of graphing this on my calculator, and I've got that function on there, and I'm going from 0 to 2. And you can see the region that we're referring to. We want to find the exact area of that region. So what we need to do is we need to set up an integral that represents the area of that region. So we're integrating starting at x equals 0, ending at x equals 2. And we're integrating the function 2x squared minus 3x plus 2. So what I want you to do right now, really quick, is just hit pause and rip through this bear and be very careful with your antiderivative and your number crunching. That is perhaps the most challenging component. And then come on back and see if we got the same thing. Alright, for my antiderivative, I added 1 to the exponent and divided by 3. So I got 2/3 as a coefficient minus x squared now, divided by 2, that's 3/2. Wow. Look at those feisty exponents. Plus 2x, bounds of 0 to 2. Alright, let's plug that 2 in. I got 2/3 times an 8 minus 3/2 times a 4 plus a 4. Close it off. Now, I love 0. Oh, we love our 0. So you just got 0 minus 0 plus 0. Very redundant. So let's work on cleaning up that first group. And let's see, 2/3 of 8 is going to be 16/3 minus, let's see, boom, boom, that turns into a 2, so I got minus 6 plus 4, 16/3 minus 2 if I combine these rascals, and that's really 6/3. So how about 10/3 for my total net area of the region that was sitting up here? Now what I want you to do is I want you to go grab your calculator, okay? And I'm going to show you a few new things on the calculator. I'm going to walk you through, hopefully, and you can find the buttons on yours as you go, and just mentally rehearse and physically rehearse pushing these buttons so that we can do it in tomorrow's class without missing a beat. But here's what we want to do. I'm assuming you've already gone to y equals and typed in the equation here. So you've already been to y equals and you typed in your 2x squared minus your 3x plus your 2. Alright, now what I want you to do is I want you to hit second quit. And what that's going to do is that's going to take you back to your home screen. Okay, so now once you're on your home screen, I want you to hit the math button, which is on the left hand side towards the top. Should be third from the bottom there on the left side. Once you're on your math screen, I want you to scroll down until you see the 9th option. The 9th option there is for FNInt. That stands for function integration. And once you hit that, and I'm assuming you have an updated calculator, it's going to take you back to your home screen and you're going to have a nice integral. And you're just going to fill everything in. You're going to fill in a lower bound of 0. And then if you hit your right arrow, I believe it takes you right up to your upper bound. You can type in the 2. Now you'll notice what I've got. I've got my y1 there. You actually could type in the 2x squared minus 3x plus 2. You could. But what I did is I hit the vars button, which is right underneath the down arrow. And then after I hit the vars button, I went over to yvars. Okay. And let's see, after I hit yvars, choice number 1 was for function. I hit enter right there. And then choice number 1 again was for y sub 1. And that's a trick. We're going to use that a lot in the future, so that's why I wanted to introduce you to it tonight. And once you hit enter, let's see, you should get an answer of 3.3 repeating. And then I hit the math button and had the calculator convert it back to a fraction. I got 10/3. That does, yes, that checks. It matches the answer I got by hand earlier. Now I want to show you one more trick before we call it a night. Let's go back to your graphing screen, okay? Hit graph so you can see, you're probably in Zoom Standard maybe, or you could tweak the window a little bit to fine tune it. I think I had like a y min of -1, an x min of -1, and so forth. But anyway, I want you to go to the second trace button, okay? Second trace, not just trace, second trace. That's going to take you to the blue calc menu. And when you get to that calc menu, I want you to scroll down to number 7. We're going to choice number 7. That's your integration. Once you hit enter, the calculator is going to ask you a couple of questions. It's going to ask you for a lower limit, and I just literally typed in 0 right now. I didn't move the cursor or anything. I just typed in 0. I hit enter. It then asked me for an upper limit. I typed in my 2. I hit enter, and then it, very interestingly, it shaded in the region for us and gave us a numerical answer of 3.3 repeating, which again is equivalent to our 10/3. So I want you to be comfortable with the calculator. We're going to build some calculator skills over the next couple of weeks, and this is one of the main ones. So hope you had a good night, and we'll see you tomorrow.